In this video, we will be looking at different techniques to solve more complicated equations, specifically equations that have rational expressions or things that look like fractions, or radical expressions, things that are square roots or cube roots. Let's talk first about the rational equations. You may remember from a previous algebra class that when you have any kind of an equation that has fractions in it, one of the strategies that you learned was to make the denominators the same. And we do that by talking about the least common denominator. In this example, the least common denominator would be 15. And the way that we learned to make these two denominators the same was by multiplying both fractions by a form of 1. So maybe I would multiply the first fraction by 5 over 5, and the second fraction by 3 over 3. So that I could have the same denominator for both fractions. Once they were the same, I could combine them. And then to continue solving, I would divide by 2, or maybe in this case, I would multiply by a half, just because it's a little easier to see since I've got a fraction on the left-hand side. And I would end up with 8 over 30 equals x, or if we simplified that, 4 over 15 is equal to x. I'm going to suggest that maybe we think about this in an alternate way. We're still going to use the least common denominator of 15, but instead of making both of the denominators the same, we're going to use that LCD to get rid of the fractions completely. And we do that by multiplying both sides of the equation by 15. The 15 is going to multiply by both fractions separately. When you have a whole number that's multiplied by a fraction, technically the 15 in this case only multiplies by the numerator. But it's then going to be divided by that 3. So if we think about 15 times a third, it's the same as 15 divided by 3, which would be 5. Similarly, 15 times 1/5 is the same as 15 divided by 5, which is 3. And on the right-hand side, we get 30x. So I have that 8 is equal to 30x. Dividing both sides by 30, I'm ending up with the same answer that I got before. 4 over 15 is equal to x. In this example, it seems like it's about the same amount of work, but in the examples we're going to be looking at next, we've got variables in the denominator, and so it makes it less complicated if we use the method of clearing denominators rather than getting denominators to be the same. See that they're telling us to solve an equation like this, we want to multiply both sides by the least common denominator, and that'll have the effect of clearing the fractions. In this particular example, the least common denominator, which comes from the 3 and the 2, is going to be 6. So the strategy that I'll use is to multiply both sides of this equation by that least common denominator, which is 6. The 6 is going to distribute to both of these fractions. When I multiply a whole number by a fraction, technically, we do a little side work over here, the 6 is going to multiply just by the numerator. But then that 3 is divided in the bottom. Multiplication and division are in the same level in order of operations. Remember your PEMDAS? Multiplication and division are equal to one another. And so we can switch the order here, and rather than multiplying, we can actually divide first. So I'm going to think to myself, 3 goes into 6 twice, and then I'll multiply that 2 by the t plus 1. Going to the second fraction, I'll do the same thing again. I'll say that 2 goes into 6 3 times, and then that will get multiplied by the t minus 1. On the right-hand side, we have 6. I'll distribute the 2 and the negative 3 here. Make sure that you remember that negative sign gets distributed so we get a plus 3. So then we have negative t plus 5 equals 6. Negative t equals 1, subtracting 5 from both sides. And so then t is equal to negative 1. We think this is our answer. Let's just double check to make sure that our answer is correct. So our first fraction was t, we'll put negative 1 in there. Negative 1 plus t over 3. And then we'll have negative 1 plus 1 over 2. And we want to know whether that's equal to 1. This should be a 1, right? Negative 1 plus 1, negative 1. Goodness, that's bamboozled. Let's start that over. Go back. Negative 1 for t plus 1 over 3, first fraction. Negative 1 minus 1 over 2. And we want to know if that is equal to 1. I think that's correct. So for our first fraction, we're getting 0, right? 0 over 3. For our second fraction, we're getting negative 2 over 2. Yeah, that looks like it's going to end up equaling 1, right? Because it'll be a negative 1. That's correct. Yay. So the answer that we got here is correct. I just want to double check that it actually works in the original equation. All right, let's do another example. Some of you may remember an example like this, and one of the shortcuts that we learn sometimes in algebra classes is to cross multiply. And that's a term that I don't particularly care for, only because it only works in one situation, and this is the situation that it works in. Cross multiplying only works if you have two fractions with two rational expressions. I'm not going to cross multiply, but I'm going to show you why cross multiplication works, and this is the example that it works in. The last example that we had, there were two fractions and then something else on the other side of the equal sign, so cross multiplication would not work. And so sometimes students will remember cross multiplication and use it in the wrong place, so that's why I don't like to teach that. The method that we've been talking about is to multiply by the least common denominator. In this case, I have two different denominators. I have x minus 1 and I have x minus 3. and they don't have anything in common. So the least common denominator for this is going to be both of those two numbers multiplied together, x minus 1 times x minus 3. So I will multiply both sides of this equation by that least common denominator. X minus 1 times x minus 3, and x minus 1 times x minus 3. Now notice I kind of wrote it up above to remind us that technically it gets multiplied by the numerators, but before we multiply, we want to see what it can cancel in the denominator. And if we've done this process correctly, our next line should end up with no fractions at all. On the left, we're going to have the x minus 1 and the x minus 1 cancel. And so it looks like we have x minus 3 multiplied by 2x. On the right, the x minus 3's will cancel, and we end up with 5 multiplied by x minus 1. Now going back and looking at our original, if we had cross multiplied here, we would have ended up with this line that we have here. And just again to overemphasize, this will only work if you have exactly two fractions with an equal sign in the center of them, and that's the only case. And since that's the only time that it works, I like to teach this clearing by the least common denominator method because that will work with all problems that you come across. All right, let's continue here. So multiplying this out, we get 2x squared minus 6x equals 5x minus 5. Because I have a term that is squared, I know that I have a quadratic, and the way we solve quadratics, as we saw in the last section, is to move everything to one side and 0 on the other. So I'll subtract 5x from both sides, and then I'll add 5 to both sides. Now I'm going to factor this. I'm thinking about 2 times 5, which is 10, and I want to get to negative 11. So I know I'm going to have a minus 10 and a minus 1. So I think if I put a 5 here, that'll give me minus 10. And if I put a 1 here, that'll give me another minus 1. So minus 10, minus 1, that's that minus 11 in the middle. So that tells me that either x is equal to 1/2 or x is equal to 5. I need to go back and check both of these answers because in these types of equations, sometimes one of the answers or both of the answers don't work. For example, if we had ended up with 1 as one of our answers, we would have had to reject it because 1 is not in the domain of this first function that I have. It would make the denominator 0. Similarly, if I ended up with 3 as one of my answers, I would have to reject it because 3 is not allowed to be plugged into these fractions. All right, so let's check over here. Let's start by checking x equals 1/2. I'm going to plug 1/2 into the original. Okay, so I've plugged in 1/2 everywhere that I have x. 2 times 1/2 is 1. 1/2 minus 1 is going to be a negative 1/2. 5 over 1/2 minus 3 is negative 2.5. If I divide this out, this should be negative 2. And this is also negative 2, so that answer works. Let's go over here and check x equals, what was our other answer? 5. So I'm gonna plug 5 in now for x. So 2 over 4, oops, I forgot to multiply here, sorry. 2x, there should be a 5 here. Let's see, double check. So 2x over x minus 1, good. 5 over x minus 3, okay, that's good. So we're looking at 10 over 4, and we want to know if that's equal to 5 over 2. Yeah, that looks like it works. So in this particular example, it looks like both of these are answers that will solve that original equation. Here's an example where that cross multiplication won't work because I have 3 different expressions together. Let's think about what the LCD is here. We have x squared minus 9, which is the same as x plus 3 times x minus 3. And in the other two fractions, I have an x minus 3 and an x plus 3. So I think that if I multiply everything by this, I should be able to clear all of those fractions. I'm going to multiply both sides of this equation by x minus 3 and x plus 3. For the first fraction, this entire denominator will simplify with this entire this entire x minus 3, x plus 3 will wipe out the entire denominator that I have there. So I just have 2 left. For the second fraction, we're going to have the x minus 3 cancel with the x minus 3. So we have still an x plus 3 multiplied by 5. On the right-hand side, I have the x plus 3 and the x plus 3 canceling. So we have 3 multiplied by x minus 3. So this is 2 plus 5x plus 15 equaling 3x minus 9. Let's get all of the x terms together on one side. If I subtract the 3x, I'll have 2x over here. And move all the numbers to the right, I'll have negative 9 minus 2 minus 15. So 2x is equal to negative 26, or x is equal to negative 13. All right, let's check this. Let's check x equals negative 13. I have 2 over negative 13 squared. 5 over and we want to know if that equals 3 over this. So this is 2 over 169 minus 9 is going to be 160. 5 over negative 16. And that would be negative 10. This is the same as 1 over 80. If I change this second fraction to be over 80, multiply both things by 5 over 5. Let's do negative 5 over negative 5. We'll get minus 25 over 80. And then multiply this guy by negative 8 over negative 8. I'm just trying to get all of the denominators to be 80 so I can compare them. Negative 24 over 80. Yeah, this is going to work. 1 minus 25 will give me that negative 24. So it looks like this works. And our solution here is x equals negative 13. All right, one more example of this type. In this case, our least common denominator is going to be x times x plus 2. If I multiply that out, I get x squared plus 2x, and I can see that that will clear the denominator on the right-hand side. So I will multiply both sides of the equation by that least common denominator, x times x plus 2. For the first fraction, the x plus 2's will cancel, and we have x multiplied by 3x. For the second fraction, the x's will cancel, and we'll have x plus 2 multiplied by 6. On the right-hand side, the whole denominator is going to cancel with everything, and we'll just have 12. All right, multiplying this out, it looks like we've got a 12 on both sides that'll cancel. So I have 3x squared plus 6x equals 0. Let's factor out a 3x. So I'm getting that either 3x is equal to 0 or x plus 2 is equal to 0. For the first equation, x is equal to 0, and for the second equation, x is equal to negative 2. Let's look back at our original equation. In this particular case, if I look at the denominators that I have, I'm not allowed to have x equaling 0, right? Because of the denominators that I have here. X cannot be equal to 0 because of this first fraction. And x can also not be equal to negative 2 because of this fraction. So because those are the two answers that I got, I actually end up in this case with no solution. I need to reject both of these answers. They're not in the domain. So in this case, I get no solution. In these problems, sometimes you'll end up rejecting one of the answers or both of the answers, as in this particular example. So you just want to make sure you check at the very end. All right, the next set of examples are solving equations that have radical expressions, square roots in this example. And this is telling us that if we have two things that are equal, their square roots are also equal, or vice versa. If you have two things that are raised to a power, two things that are equal, raising them to a power will make them equal. So you could raise them to the second power or the third power, or take the square root or the cube root or the fourth root, etc. Now, I'm just going to go through examples because the way that you solve this is sort of a little confusing at first. You want to see examples. The main thing that we do is isolate one of the square roots on one side, and then you square to get rid of the radical symbol. This first example is really simplistic. We have a square root on one side, a number on the other. And so what we'll do is we'll just start by squaring both sides of the equation to clear that square root symbol. As long as I do the same thing to both sides of an equation, I'm always fine. The square root and the square cancel each other, so we have 2x minus 5 equaling 4. Add 5 to both sides, so 2x is equal to 9, and then divide by 2. X is equal to 9 over 2. Again, similar to the examples we were doing before, we always want to check our answer. So let's plug in 9 over 2 for x. And we want to know whether that's equal to 2. The 2 divided by 2 is going to cancel, so we'll just have 9 minus 5. Yeah, that's going to be the square root of 4, right? So I think this is going to work. So 9/2 is our solution. Here's another example that's similar, but it has this extra component sitting here. Anytime that we're going to square both sides of an equation, we want to make sure, if we can, to move anything away from the square root symbol before we do that. So we'll start by adding 3 to both sides before we get started. So I'll have the square root of 2x plus 1 equals 6. And now I can proceed the way that I did in the last example by squaring both sides of the equation. Subtract 1 from both sides, and then divide by 2. If we check this answer, it'll end up making the equation true. And so we know that that's a good answer. Following that same type of example, let's subtract 5 from both sides before we get started. Again, we're moving everything away from the radical symbol. But when we go to square now, the right-hand side is more complicated. Before, it was just a number. The left-hand side is easy because the square and the square root symbol will cancel each other. But on the right-hand side, I've got to think about x minus 5 multiplied by x minus 5, right? We square the first term, we square the last term, and then we take the two terms, multiply them together, and double. So minus 10x. Again, this is a quadratic, and to solve, I get everything on one side, 0 onto the other. So I'm going to subtract x and add 3 to both sides. So it looks like I'm getting x squared minus 11x plus 28 equaling 0. This can be factored. Into x minus 4, x minus 7. So x is either equal to 4 or x is equal to 7. All right, let's check our answers here. Let's start by checking x equals 4. One of the things that happens sometimes when you square a square root is it creates artificial Solutions. This happens a lot in trigonometry when you're solving equations. If you have to square both sides of an equation to use some of the identities, sometimes you get answers that are not within the true answer key and you need to reject them. So I think that's going to happen in this example. Let's plug 4 into the original. We'll have 4 minus 3 plus 5, and we want to know if that's equal to 4. So we have the square root of 1 plus 5. This is not going to equal 4, is it? So we are going to reject this answer. This answer does not make the equation true. Let's check x equals 7. So we have 7 minus 3 plus 5, and we want to know if that equals 7. 4 minus 3, or 7 minus 3 can be square root 4 plus 5 equals 7. Yeah, this one works. So in this case, our answer is just going to be x equals 7, and we're going to reject this answer. Oh no, this one is very complicated. It's got 2 square root symbols in it. Remember that when you square something, you square the first term. If you have 2 terms, you square the second term, and then you multiply these 2 together and double. So just in looking at this, that looks really terrible, and I don't think that I want to do that. So instead, what I'm going to do is move one of the square roots to the other side. When you have 2 square roots like this, you typically have to repeat the process of squaring twice. So I'm going to show you 2 examples like this. The first step is to move one of the square roots to the other side of the equation. Okay. Now, similar to the other problems that I've been doing, I will square both sides of this equation. And the left-hand side's pretty easy, right? That's just x minus 3. It's the right-hand side that now has become complicated. So again, the process is I square that first term. 5 squared will give me 25. I square the last term. That's going to be x plus 2, right? That'll just remove the square root symbol. And then for the middle term, I'm going to multiply these 2 together, and I'm going to double that. So I'll have minus 10 times the square root of x plus 2. Again, I multiply those 2 terms together, and I double. Okay. Let's move, now we're going to kind of start the process over, move everything away from the square root symbol onto the left-hand side. So I'll subtract 25, subtract x, subtract 2. So I'm going to have x minus x is nothing. And then I'll have negative 3, negative 25, negative 2. That's going to be a negative 30 over here. So that variable went away there. On the right-hand side, what I'm left with is the negative 10 times the square root of x plus 2. I don't have to, but just because I can see that it's going to be easy, I'll divide both sides by negative 10. And then I'll have 3 equals the square root of x plus 2. That simplified pretty nicely, didn't it? Now if we square both sides, we get that 9 is equal to x plus 2. And so for final answer, I'm getting that x is equal to 7. You can go back and check, but this answer ends up being correct, x equals 7 for this original equation. All right, last example, I just wanted to do one more like this with 2 square roots just because it's a little bit more complicated, a few extra steps. We start by moving one of the square roots away, so I'll add the square root of y minus 3 to both sides. So on the left, we'll have 2y minus 5. And on the right, we have 1 plus the square root of y minus 3. I'm going to square both sides of this equation. And the left-hand side is much easier. The square root and the square symbol will cancel each other, and we just get 2y minus 5. On the right-hand side, I square the first term. 1 squared will be 1. Then I square the second term. That just removes the square root symbol. And then to get the middle term, I multiply these two things together and I double that. So this will be plus 2 times the square root of y minus 3. I'm going to move everything that's not with the square root symbol over to the left-hand side. So we'll subtract 1, subtract y, and add 3. Minus 1 minus y plus 3. Let's combine things together. 2y minus y will give me just y by itself. I've got negative 5, negative 1, and plus 3. That's going to be a minus 3. And on the right-hand side, what's left is 2 times the square root of y minus 3. In the last example, at this stage, I divided by the number that was in front of the square root symbol, but that's because it divided nicely into what was on the left. In this case, if I do that, it's going to create fractions, and so I'm just going to leave it there for the moment. It's not going to hurt things too much. Because at this point, what we're going to do is square both sides of the equation. On the left, we have y minus 3 times y minus 3, right? So we square the first term, square the last term, multiply the two terms together and double, so minus 6y. On the right-hand side, we're going to square the 2, which will give me a 4. And then we're going to square the square root, which is going to be y minus 3. All right, let's combine everything on one side because we've got a quadratic that we need to probably factor here. Y squared minus 10y plus 21 equals 0. This factors into y minus 7 and y minus 3. So our two solutions are y equals 7 or y equals 3. You can go back to the original and check both of these, and they both work in the equation. All right, if you have questions, you can send me an email. Thanks for watching, and I will see you in class.